In this video, we're going to take a look at exact numbers and exact conversion factors because on your mud cards you indicated that you were having a little bit of difficulty identifying those. Let's begin with what exact numbers are. Exact numbers are numbers that have infinite or unlimited significant figures. They are important because they can never limit the sig figs in a calculation. And as we've said before, you want to fight for every sig fig you can keep. So how do we identify an exact number? Well, it counts quantized objects. It's the counting that's important. This means the objects cannot be cut into parts. And this means that measurements are almost never exact numbers. Measurements don't really count, usually. So let's take a look at some values. Which of the following are exact numbers? Your options are 5.0 times 10 to the 24th zinc atoms, 3.33 grams of sulfur, 18 eggs, or 2.5 cups of flour. The zinc atoms and the eggs are both exact numbers because you can't have half an atom and you can't have half an egg. The 3.33 grams of sulfur and the 2.5 cups of flour, on the other hand, are measured values and are non-exact numbers. These would both limit our sig figs. Now let's turn our attention to conversion factors. Conversion factors allow us to convert a value from being defined by one unit to being defined by another unit. They're very important in chemistry. And you can readily identify them because they have compound units, something per something. Let's take a look at a couple examples of just conversion factors. For example, 12 inches in a foot. 6.0221 times 10 to the 23rd atoms in 1 mole, or 1,000 milliliters in 1 liter, or ethanol's density being 0.789 grams per milliliter. These are all conversion factors. Exact conversion factors do not limit your sig figs, but inexact or non-exact conversion factors can, depending on how many sig figs they have. Let's look at a few identifying features. So how do we identify exact conversion factors? One key way is if that conversion factor is a definition. If we are defining another unit as being a certain number of a particular unit, then that is an exact number. An important thing to note is that conversions between SI and imperial units are never exact, and here's why. Any measured conversion factor is not exact. Anytime we have to make a measurement, we are limited by the precision and accuracy of our measurement technique. Therefore, we can't assume that these are exact numbers. We frequently have to measure the differences between SI and imperial units, and so those conversions are never exact. So looking at our list of 4 conversion factors again, which of these are exact conversions? It would be the 12 inches in a foot and the 1,000 milliliters in 1 liter. Both of these are definitions. Avogadro's number is a measured value, and so is the density of ethanol. So these are not exact. Let's take a look at some examples of exact conversions that are especially applicable to chemistry. Mole ratios obtained from chemical formulas or chemical equations are always exact. And again, this comes back to the fact that you can't have partial atoms. Let's look at an example. This is the equation for the combustion of ethane. C2H8 plus 4O2 becomes 2CO2 plus 4H2O. Here are some of the conversion factors that we could pull out of this. For instance, 1 mole of C2H8 contains 8 moles of pure H, or 4 moles of O2 will produce 2 moles of CO2. It's worth noting that we could also say these conversion factors about molecules. Here's an example calculation. 3.5 moles of C2H8 will make how much H2O after it combusts? You can pause the video and try this one out yourself. All right, let's take a look at the answer. we're going to start with our 3.5 moles of C2H8. Then, from our chemical equation, we can pull out that 1 C2H8 will make 4 H2O, giving us our conversion factor. This mole-to-mole conversion is an exact number, so it won't limit our sig figs. 3.5 times 4 is 14. And our weak link over here has 3.5, so that's 2 sig figs. So we have 2 sig figs in our final answer. But what about non-exact chemical conversions? So the 3 examples here are molar masses, which we learned about in Chapter 2, molar heats, which we'll learn about in Chapter 9, and molar volumes, which we'll learn about in Chapter 10. These are never exact because we have to measure them. Molar masses are calculated from atomic masses, which are measured. Molar heats, or how much energy a chemical releases when it forms, is measured using calorimetry, and the molar volume of a gas is measured by simply measuring it. Let's come back to our combustion equation and work through another example. How many grams of CO2 are produced from burning 34.8 grams of C2H8? Go ahead and pause this video and give it a try. Let's take a look at our train tracks for this. We're going to begin with our 34.8 grams of C2H8. We know from our map of stoichiometry, another video I've posted, that we need to convert our grams of ethane to moles by using its molar mass, which I have calculated here. Now that we're in moles of ethane, C2H8, we can convert that into moles of CO2 using the mole ratio we pull from our balanced chemical equation. In this case, 1 mole of ethane becoming 2 moles of CO2. We can then take the moles of CO2 and convert it to grams of CO2 with its molar mass. Let's consider where the weak link might be in this calculation. Well, we know that our mole-to-mole ratio is an exact conversion. But what about these moles and grams steps? Well, these are non-exact conversions because molar masses are non-exact conversion factors. So these could be our weak link. Let's look at the other values we're using as inputs. It turns out our original 34.8 grams of C2H8 is the weak link because it possesses the fewest significant figures, and we're doing all multiplication and division. So let's crunch the numbers. After we crunch the numbers, our original answer is 95.845 grams of CO2, but we need to round to 3 sig figs, so the final answer is 95.8 grams of CO2. So to recap, exact conversions are things that are definitions, things that are counting quantized objects. And that can include the mole-to-mole ratios that you get from a chemical formula or from a chemical equation. Non-exact conversions are any values that we have to actually measure, and this includes molar masses or densities. All right, guys, I'll see you on Monday.